Okay, so we can start. We're happy to have Andrea from SISSA to tell us about aspects of self-duality, symmetry, holography, and anomalies.
Hi, thank you everybody for coming. And in this talk, I would like to give an overview on several aspects of what I would call self-duality symmetries, and we'll explain what I mean by this. I've been thinking about these problems over, let's say, the last year with this set of collaborators. My supervisor at SISSA, Francesco Benini, Christian Covetti is now a postdoc in Oxford, Giovanni Galati is now a postdoc in Brussels, and Giovanni Rizzi is another grad student in SISSA. So I'm sure that it is even not necessary to motivate that symmetries in physics and in quantum field theory are very important, allows you to give powerful constraint on the dynamics. And often the typical problem that you have in both in high energy physics and in condensed matter is start from some UV microscopic description of your system, and you ask for long distance questions, and this is often a very complicated problem. You can have strong coupling, and there are few things that you can compute, and symmetries are a quite powerful tool in this analysis because they put constraints on what are the possible outputs at low energy. And so the slogan is that the more symmetry you have, the more control, the more powerful tool you have. And in the recent years, there have been a lot of revival in this kind of reasoning because of the discovery of new and generalized kind of symmetries. Some keywords are higher from symmetries, in which the charged object, instead of being local operators particles, are extended object and extended operators. And the more drastic generalization that is becoming very popular in the last years is the one of non-invertible symmetries, in which you drop out the unitarity of your operator and you drop out the condition that your symmetry is described by groups. And all these generalizations are based on a simple but powerful observation, which is how to define intrinsically symmetries in quantum field theory, similarly to how you define them in more standard quantum mechanical systems. Indeed, in any quantum system, a symmetry is an operator computing with the Hamiltonian. But when you have local quantum field theories, the Hilbert space becomes an Hilbert space associated to a certain space-like slice, and operators become operators associated to this slice, which is of codimension 1. So all the operators can be thought of as extended codimension 1 operator in your space-time. And this equation is just telling you that these operators, the one implementing the symmetry, can be slide along time and nothing will change. But then when you have a relativistic quantum field theory, local in the dimension, there is no preferred time, there is no preferred direction in which you can slide your operators, and so this operator describing the symmetry in this set of theory is a topological operator, meaning that you can deform it in any direction and in any way, and it will not affect the correlation functions. So the slogan that has become popular in the last years is that symmetries in quantum field theory are the same thing as topological operators or defects. And as you see, in ordinary symmetry, these are codimension 1 extended operators. And starting from this, you can cook up several generalizations by dropping few of the assumptions that you have here. And for instance, if you drop codimension 1, you will have higher codimension operator acting on extended object, and this is the notion of higher from symmetries. And if you drop the assumption that symmetries are described by groups, in particular, it is no longer necessary that they are implemented by unitary operators, then you arrive at this more drastic notion of non-invertible symmetries, in which the operators are not longer labeled by group element, but can form a more generic fusion algebra. When you put together two operators, instead of getting a third operator labeled by a group element, generically you can have something like a fusion algebra. here I'm not being very careful in explaining what are the meaning of all these symbols. There are several possible generalizations, but okay. And moreover, another aspect which is very important is that okay, symmetries are powerful because they must be matched along the RG flow. They describe like the topological sector of any quantum field theory. But sometimes, on top of the group structure, or more generally this kind of fusion algebra, there might be further and more subtle data associated to the symmetry, which still they must be matched along the RG flow and for any continuous deformation. And I will generically refer to this kind of more subtle data as anomalies. They do not affect the group structure or the fusion algebra, but these are further data on top of this, which should be matched. And for ordinary symmetries, let's say for ordinary invertible symmetries, we have a theory T in D dimension with an ordinary invertible symmetry G. An anomaly is the statement that when you couple your theory to a background gauge field for the symmetry, and you perform a background gauge field transformation, generally you would expect to leave the partition function invariant, but sometimes this is not the case. There can be mild violation of this by a phase which can be expressed as a local integral. This alpha is called the anomalous phase. It is constrained by several consistency conditions with the group G, and that's also several identification because you're always free to add to your action a local counterterm depending only on background fields. And so it turns out that typically this alpha are actually classified by some cohomology problems. What really matters is the class of this. Okay? And this generically we refer to as cohomology groups. They are typically discrete. So these anomalies are discrete data and cannot vary with continuous deformation, in particular cannot vary along the RG flow. So they give you stronger constraints on the dynamics of your quantum system. And here there is one point that I want to emphasize, because at the end I will describe a generalization of this for non-invertible symmetries. For non-invertible symmetries, this kind of holographic generalization, still we don't know a concept of what is a background gauge field for the symmetries. So it seems hard from a technical point of view to say what is an anomaly for that. However, you see from this definition that when you have a non-trivial anomalous phase, you cannot consistently sum over background gauge field. So an anomaly can be described as an obstruction to gauging. And in this way, in this kind of definition, it is possible to generalize anomalies to non-invertible symmetries. Indeed, even if we don't know a concept of background gauge field for non-invertible symmetries, we have a sort of generalized notion of what does it mean gauging in non-invertible symmetries. So in this way, we are allowed to go beyond, and I will discuss what do I mean at the end of the talk. But now I first want to tell you about what are the kind of symmetries that we'll be talking about, namely self-duality symmetries. And before giving the general picture, let me start from an example, which is the simplest one, which is Maxwell theory in 4 dimensions. Very trivial theory, just the theory of a free photon. It is well known that this theory has electromagnetic duality. Electromagnetic duality essentially maps the field strength, the dual field strength, the complexified gauge coupling, putting together the electric charge and the theta angle to -1 over tau, and Wilson lines to Toft lines. So for generic value of tau, this electromagnetic duality gives you 2 different descriptions of the same physics. But what happens, and it is special, that at tau equal to I, these 2 descriptions are formally identical. So this electromagnetic duality is turned into an actual symmetry of a single physical theory. It's a Z4 symmetry, 0-4 symmetry. Okay? And following the paradigm that symmetries are described by topological operator, this will be implemented, since this is a zero-form symmetry in 4 dimensions, by a 3-dimensional topological defect that we will call n. This is associated to a 3-dimensional manifold. And what it does is that if you have a Wilson line here, you can slide the topological defect through the Wilson line, and what you will get is a Tooth line.
I'm a bit confused. So you're talking about free Maxwell symmetry.
Yes.
Why the value of coupling then plays any role?
Yeah, this is a good question. It is. I mean, actually, the value of the electric charge can always be reabsorbed into the gauge field. But if you reabsorb it, you are changing the Dirac quantization condition. So after you fix a Dirac quantization condition, then the value of the coupling is meaningful.
But Dirac quantization condition, here you mean just because there are no charges in your theory, right? But you mean that you talk about free comp Q1, right? And
Yes, free comp Q1.
Yeah, specify the spectrum of Lyell.
Yes. Mm-hmm. If you are in R Maxwell, this makes no sense. Okay. So, and you can check easily from these definitions that if you take the orientation reversal and you fuse it with n, you get 1. Right? So this is a very standard invertible zero-form symmetry. Now, but you can say, who cares about Maxwell theory? It's very boring. It's a theory of a free photon. Let's do a more interesting example. And since we want to have some kind of duality of this kind, let's discuss n equal to 4 super Young weights. 4 dimensions. Right? And this theory also has a similar duality, but this is an interacting theory. This is the so-called Montoya-Olive duality. And you may want to try to play the same game at tau equal to I, but you notice the following: that if you start from SUN, super Young mills, certain coupling tau, then maybe you think that you get SUN coupling minus 1 over tau, and I can play the same game. But this is wrong for a factor of p. You're really changing the gauge group. This is not SUN. It should be SUN divided by Gn. So even at tau equal to I don't get two equivalent, two formally equal description, and so this does not become a symmetry immediately. But the idea to overcome this problem is that I can compensate this by the gauging of a one-form symmetry Gn. This is a gauge theory with, let's say, matter only in the adjoint, so it has a Tn one-form symmetry, and this changes the global structure from SUN to PSUN and vice versa. And to describe more concretely what I'm gonna do, this is the so-called half gauging construction. It's a way to produce a topological defect like this, but the procedure is the following. You divide your spacetime into parts. In one part, you put the SUN theory, having tau equal to I, and then you put an interface which separates this theory by the one in which you are gauging the one-form symmetry. Here you gauge the one-form symmetry. So here you have PSUN, having tau equal to I.
Gauging one-form symmetry, is it equivalent to going to PSUN?
No, this is not equivalent because the Montoya-Olive duality changes the structure of the gauge group, but also acts on tau.
No, I'm not asking about the change. Just because when you say gauging this center symmetry,
Yes.
is it the same as going from SUN
Yes.
to
PSUN?
PSUN?
Yeah, right. But then, since we are at tau equal to I, which is a special point, what happens is that here I can apply Montoya-Olive duality. And this is again SUN, counting tau equal to I. So here, on both sides, I really have two formally equivalent theories. And this gauging interface, which again we call M, it's turned into an actual topological defect of your theory, right? So it seems we solved the problem, it's something like what we did in the Maxwell theory, but you immediately notice that there are some differences. Because Montoya duality still maps Wilson lines of SUN to Booth lines of PSUN. But now, since we are going to from SUN to SUN again, what happens is that the Wilson lines are genuine line operators of the SUN theory, but the Booth lines are not. The Booth lines only exist attached to a surface defect implemented in one-form symmetry. So in a certain sense, not in a certain sense, it's actually a good analogy. It's not an analogy actually. They live in the twisted sector of the one-form symmetry. So what this N is doing, it is mapping the untwisted sector to the twisted sector. So it's kind of weird. It cannot be an ordinary symmetry. And indeed, what you can do is to try to compute again this fusion of N and this orientation reversal. They will give you the quick argument, this out from SUN. Here we are doing this half gauging, equal to PSUN, with this N. And then the orientation reversal, undo the gauging. So you go again to SUN. And when you fuse the two, you get SUN on both sides. And since here you were gauging the one-form symmetry in this lab, what you get here is not a trivial defect, but it's a three-dimensional defect. It's called a condensation defect, which is obtained by gauging the one-form symmetry not in a region, but on a three-dimensional submanifold of your spacetime. This is called a condensation defect. It is a non-trivial defect. It is different from one. And you realize that then the symmetry becomes a non-invertible symmetry. There is no defect which if I fuse it with N, I get 1. The best that I can do is to obtain this condensation defect. Right?
Sorry, I'm quite slow, but so this is valid at any value of the coupling now. Like you're not using Montoya duality or anything.
No, if I don't use Montoya duality, this N is not a symmetry of the theories. It's an interface between two different theories.
Okay, so at tau equals I, what happens when I go from one side of the condensation defect to the other between these two SUNs once I fuse the two?
Now, if you look at the argument for the fusion, it looks the same, even at tau different from I. But the point is that N is not a topological defect of one theory. It's an interface mapping one theory to another. You can construct topological interfaces between different theories, but this is not a symmetry of a theory.
Okay, so yeah.
And still you can fuse topological interfaces and you get this fusion rule. This is valid at any value of tau, but the symmetry exists only at tau equal to I.
Actually, I got the opposite question. So, why does it become topological? Can you explain it?
Okay, here I was giving the quick argument, but you can argue more precisely that actually when you do this gauging, since you're doing a gauging in half space, you have to be careful about boundary conditions for the gauge field. And you can argue that if you put Dirichlet boundary condition for the gauge field on the interface, then you can move a bit the interface and nothing changes.
Intuitively, you can think about the topological properties coming from the fact that the stress tensor is transparent to this interface. And because the discrete symmetry, the symmetry of the stress tensor, and you're doing a discrete operation, it does not change the stress tensor, it stays transparent.
It's very important that you put Dirichlet boundary condition. If you don't put Dirichlet boundary condition, you don't get a topological interface. Good.
Is only Dirichlet?
Sorry?
Only Dirichlet or?
Only Dirichlet, yes. And only for discrete symmetries. If you try to play the same game with continuous symmetries, you don't get the topological defect.
There's some slight more freedom in the sense that you can stack with the TQFT.
Sure. You are always free to take a topological defect, stack at the coupled TQFT, and you get a new topological defect. But its action on all the operators of the theory are the same because the TQFT is decoupled.
What happens when you fuse two ends?
When you fuse two ends here, you mean?
Yes.
And you mean not with N bar, right? You get n times n turns out to be again the condensation defect, but you also have charge conjugation. Because as duality in n equal to 4 super Young Mills, also in Maxwell theory, that does not square to 1, square to charge conjugation. So this is why it is Z4 and not Z2.
And this two come like when I do 3 ends, I don't know.
Yeah, then you can continue, right? Because you know how to fuse C with N, because C with N is N bar, so you can work out all the possible figures.
And fusion of C's?
Fusion of C's with itself is something like this. C times C is again C. Is a projector. So this is why it is a non-trivial. I mean, here essentially you see that for going from one side to the other, you are mapping untwisted sector to twisted sector. But then you come back together. You come back, and essentially you are kind of losing information. So you are projecting on something. Good. So there are several questions that could arise at this point. There are several questions that could arise if you want to answer. Talk. So we generalized a bit this procedure, going from Maxwell to n equal to 4, but you can ask whether this slightly different procedure is just a subtlety or not, and there is no actual consequence. And moreover, you can ask whether this symmetry implies dynamical consequences. And last but not least, since I was talking about n equal to 4 super Young Mills, and I'm telling you that at tau equal to I there is another symmetry, you can ask what is the holographic counterpart of this. I will try to give an answer to all these questions. Just to anticipate, the answer to the first question is no. It is definitely not a subtlety. This is because the answer to the second question is yes. There are dynamical consequences of this symmetry, and moreover, these dynamical consequences are really of the form that it is really this apparent subtlety that sometimes imply very strong constraints on the dynamic of any symmetry-preserving RG flow. For instance, in some cases, it is really this additional procedure of dual gauge that you can do that for certain value of n implies that any symmetry-preserving RG flow must end in a phase which either breaks spontaneously the non-invertible symmetry or must be gapless. So you see that this can be understood as an anomaly, but even if the symmetry is discrete, sometimes this anomaly, except if we want to spontaneously break the symmetry, cannot be met by a gap realization. It must be met by a gapless realization. And interestingly, the analysis of the dynamical consequences is strongly interrelated with the holographic interpretation. So I will start from explaining what is the holographic counterpart of this. But before actually doing it, just want to open a small parenthesis to tell that this half-gauging procedure can be generalized in many cases, and there is a huge landscape of theories with this duality defect. You can consider a theory in any even dimension, d equal to n, which has an n minus 1 form symmetry, given by any finite abelian group. And such that if the symmetry is non-anomalous and you gauge it, the final theory has a non-trivial duality with the original one. So this is the straightforward generalization. And I just want to make you notice that this makes sense because when you do this gauging, it is known that you always get a dual symmetry whose degree is d minus n minus 1 minus 2, which you can check that is again n minus 1, so it is the original number. And the group symmetry is what is called the Pontryagin dual, namely the group of characters. And it turns out that for any finite abelian group, this is isomorphic to A. However, this isomorphism is non-canonical, and the fact that it's non-canonical will be very important at the end, because it will require to choose some datum to identify the two, and the datum will be important in defining the category. The category symmetry and the anomalies. Right. So, but let me go back to the n equal to 4 case and discuss the holography. So, as you know very well, in holography, whenever you have a global symmetry of the boundary, this corresponds to a certain bulk gauge field. And the correspondence is such that the boundary value of the bulk gauge field is a background field for the global symmetry of the boundary. So even just from this, you understand that at least at the technical level, it seems to be a bit puzzling what is the holographic dual of non-invertible symmetry, since we don't know, as I told you, what is the concept of a background gauge field for non-invertible symmetries. But we know that there should be something happening at tau equal to I, and it's not hard to convince oneself that at tau equal to I, in the dual type 2b supergravity description, there is an emergent gauge field. Because SL2, type 2b string theory has an SL2z gauge symmetry, which for generic value of tau, if you choose a point in the gravitational modular space, it is Higgs. But at tau equal to I, it is Higgs only down to Z4. So there is actually an emergent gauge field in type 2b supergravity. At tau equal to I, you have to actually include a gauge field for this unhiggsed Z4 gauge field. Right? So, but this seems to be a very normal gauge field. But our proposal was to declare and to check that this gauge field is actually the holographic dual of this non-invertible symmetry. And it is really the interplay of this gauge field with all the other fields of the supergravity which makes the job in making this defect non-invertible on the boundary. And I will try to explain how does it arise. So to introduce the basic ideas, I remind you that what you typically do in holography is that you have this setup here, type 2b supergravity, and you want to put conformal boundary conditions, and the conformal boundary condition on the boundary of AES specify what is the dynamics on the boundary, specify what is the theory reading on the boundary. But what you are instructed to do, since you have divergences closest to the boundary, is that you put the conformal boundary condition at a certain distance epsilon. Say that you have a left and right boundary, conformal boundary condition here. Right? Then you do the standard.
Sorry, what kind of boundary condition? Like a rigid wall?
Conformal boundary condition for the supergravity.
Not like a rigid wall. No. The departure from the boundary a little bit.
What do you mean by rigid wall?
Just to understand what kind of conformal boundary condition. What do you mean with conformal?
I mean,
you just move a little bit from the boundary.
Yeah, if you move a little bit, then and you like do it in a conformal way, nothing changes, right? I mean, the boundary in standard holography, in the most known example of holography, is a conformal field theory, and it is determined by putting conformal boundary conditions to gravity. So you have the usual story. You have like do two modes. You have to renormalize one. It's the usual story. I mean, I'm just.
You mean you put in boundary condition for conformal class automatic?
Yeah. And then at the end, you will shrink by sending epsilon to 0. But as has been explained by Witter back in the days and several other papers, this is not complete because type 2b supergravity has a topological term, which in certain normalization can be written in this way. And so even when you put conformal boundary condition, you are not completely specifying the theory in the boundary. You only know about the local dynamics. You don't know about like the global form of the gauge group. And to determine it, you have to also specify when you put this conformal boundary condition, you are not killing the topological modes of B and C.
So
Sorry?
what are these?
B and C are the two form gauge fields, the Navier force and Ramon gauge field in supergravity. So because of this term, you have to also specify topological boundary condition for the topological part of these modes. And it has been argued by Presley Whitten, I think, the SUN theory is obtained by putting B equal to 0. The PSUN theory by C equal to 0. So the point is that when you put only conformal boundary condition, here this boundary only knows about the local dynamics, only know about the gauge algebra. It does not know about the global form of the gauge field. When you specify also the topological boundary condition, you know everything. But what we need is to take a slightly different but equivalent point of view. Continue here. In which instead of putting the topological boundary condition here together with the conformal boundary condition, we put it here. Indeed, after you put conformal boundary condition, there are no longer divergences, and you can really consider this lab as supporting a non-trivial TQFT, Simon's-like TQFT, 5-dimensional, right? So in this lab, you only have this TQFT, and so since this is a topological theory, you can zoom into this lab and consider only this simple setup. After you realize this, you can even forget about all the dynamics on the right. Here you effect of B supergravity. On the dynamical parts, you can forget about them. And only look at this topological term, which is the most relevant one close to the boundary since it contains the smallest number of derivatives. And so you arrive at the following setup. You have two boundaries and a topological field theory in a slab.
Sorry, I'm lost. Where is the slab came from? I thought it just epsilon was holographic cutoff, right? It's just
Yes.
went, but it's slab between what and what?
Yeah, I'm putting conformal boundary condition here, and then this was the original boundary, let's say. And instead of putting the topological boundary condition together with the conformal one, I'm putting them still at the original boundary. Yes. Then after I do this in this lab, I killed all the dynamical modes of supergravity and I remain with the topological field theory. So I will now focus only on this lab, where I have this TQFT, and all the dynamical part of supergravity is encoded in the information that here I have what I will call a relative version of n equal to 40 million minutes. So it's n equal to 40 million minutes, which only knows, however, about the gauge algebra. It does not know about what is the global form of the gauge group. It's relative in the same sense that 62,0 theories are relative. And here I will impose topological boundary conditions. And the choice of which topological boundary condition I put determines when I shrink this lab, this topological, then at the end I can shrink it.
Sorry, I don't understand. So when you mean topological boundary condition means boundary condition for the two topological fields that live in the middle.
Yes.
Yes. So but there are these two standard boundary conditions you can impose.
Yeah, there are others also.
That's my question. What are the other ones?
Yeah, the other are all for B plus RC equal to 0.
When you talk about twisting here, you have to be a little
Yes.
careful. Than before, than the example before. And now more careful you mean that there is more subtlety about just changing twisting sector or something like that.
Yes, because what you can do essentially when you go from SUN to PSUN, gauging the one-form symmetry, you can also include discrete torsion.
Yeah.
So you are putting discrete angles, and the theories correspond to P SUN R theories. Maybe it was the opposite. There are more topological boundaries. If you come out with other examples in which you don't have DN, you have more complicated group, you can have more choices. Generally, I was just mentioning two examples, but there can be various. And after you shrink, you get the physical n equal to 45 units. Is no longer relative to a TKFT, it's a physical theory. Good. So now I will focus on this TKFT in the slab. And this is an interesting five-dimensional TKFT that I can describe in terms of surface operators. This theory has a two-form symmetry. And by Gn times Gn, just as a teaser of the final part, the second factor is actually the continuation dual of the first. And this is described in terms of surface defect, surface defect of B, and surface defect of C. Right? And all the content of this TKFT is encoded in interesting breaking phases along the surface defects. The surface defect can braid directly from the action that you will get this breaking phase. So now I want to explain how the global structure of the theory arises when I put topological boundary condition. Here there is an important concept which will be important until the end of the talk. The topological boundary condition in any TKFT are in correspondence with maximal sets of mutually local objects, also called Lagrangian algebras. I will explain what do we mean. What they mean is the following. For instance, the boundary condition b equal to 0 corresponds to the following set of operators, all the surface operators of B, all of them. And imposing this boundary condition is equivalent to prescribing that all these defects inside this set can consistently end on the boundary. And moreover, in this correspondence, when this set is local in the sense that the surface defect of B do not braid among each other. The B only braid with the C, but the B do not braid with the B. And moreover, this is maximal in the sense that any other defect of the TKFT do braid with the ones in this algebra. And moreover, in this correspondence, in the boundary condition, I prescribed that all the defects inside the algebra can consistently end on the boundary, while all the others, which necessarily braid with those, cannot longer live into the bulk and are confined to stay at the boundary, and on the boundary they become topological defects implementing the symmetry of the boundary. So this is how a certain topological boundary condition determines what is the symmetry. It determines what are the topological operators of the boundary and what are the charged objects of the boundary. The charged objects are just the end lines of these surface operators. Surface operators can end at the boundary, they will end in certain end lines, and they will be like the Wilson line of the theory. While the topological surface operator will be the surface operator of C, which are stacked and are confined to live at the boundary. So the similar story is for C. Right? And all the other boundary conditions is kind of the same. There is also another complementary useful perspective on this correspondence. A Lagrangian algebra can be also understood as a gauging that you can do in the bulk, not on the boundary, in the bulk, which completely trivialize the bulk. Indeed, I can gauge it because all the defects are mutually local, and so after I gauge it, all these defects become transparent, become trivial. But all the other defects are charged with respect to the B. So they, after the gauging, they are no longer gauge invariant, and so the final theory will not contain any non-trivial defect. So Lagrangian algebra can also be described as a consistent gauging with trivialized TKFT. And I can understand this topological boundary condition as an interface between my TKFT and the version of the TFT where I gauge the Lagrangian algebra. Okay? This will be important at the end, this other perspective. Now, as I argued before, this was like the general description for any value of tau, but at tau equal to I also have to gauge this Z-form symmetry. On this TFT, you know that B and C are a doublet of SL to Z, and therefore the Z-form symmetry acts in this way. Okay, I have to gauge it, and following the general mantra, since this is a zero-form symmetry in the bulk, it will be implemented by a four-dimensional topological defect in the bulk. We call it D. Okay, this is implementing the zero-form symmetry. What I can do is to consider a situation in which this four-dimensional manifold has a boundary. So on this boundary, there will live a non-trivial operator, I call it sigma. It's called a twist operator. Twist defect. It's basically the twisted sector of this Z-form symmetry, but since we are in a topological theory, even the twisted sector are topological defects. So once I gauge this Z-form symmetry, several things happen. First, the D becomes trivial because I'm gauging it. But then the twist defect, which before was constrained to be attached to a four-dimensional defect, now is a genuine three-dimensional defect.
Sorry, where does this live? I thought you were inside of the slab, right?
Sorry?
You are still in the slab.
Yes.
So where does the twist effect live? Is it?
Sorry?
Where does the twist effect live? Like
in the slab, yes. In the five-dimensional TFT. In the five-dimensional TFT, there is this four-dimensional topological operator D. Okay? I can put it on a manifold with boundary, and on the boundary I will have this twist defect. It's a three-dimensional operator which, before gauging the symmetry, is constrained to live at the boundary of a four-dimensional operator. When I gauge the symmetry, the four-dimensional one becomes transparent, and the three-dimensional defect becomes a genuine three-dimensional defect. Okay?
Just an operator may, just defect may, in general, may not exist. So in this
Yes,
case,
sure. Yes. The reason why it exists is that this zero-form symmetry do not act on local operators. For zero-form symmetry acting on local operators, the twist operator, yes. And the third important thing that happens after gauging that I want to mention is that to do the gauging, we are introducing this additional gauge field, Z4 gauge field. And so you have additional topological operators. You have topological line operators, the Wilson line of A, and they generate the dual rep Z4, setting at Z4, symmetry. Right? This is a three-form symmetry. It's generated by line, and then
sigma is unique, right?
in this case it's unique.
Because there's only a single vacuum.
Yeah, the point is that the number of twisted sectors are in one-to-one correspondence with the number of invariant objects. And as duality in five dimensions do not have fixed points. And here the very important observation is that the three-dimensional charged object for this dual rep Z4 symmetry is nothing but the sigma. Sigma is charged. And so we're almost there with this holographic part, because now you notice the following: that once we gauge the Z4 symmetry, we have introduced an additional gauge field, and so the boundary condition that we gave before, like b equal to 0 or c equal to 0, are no longer complete. We have to put additional information about the boundary condition of A.
Sorry, in this gauging, there's other choices of discrete torsion?
Yeah, I will discuss this at the end. Okay. Yes. In principle, you can introduce it. Yes. This is another datum. I will describe this.
Okay.
Stuff. So if you put Dirichlet in a boundary condition for A equal to 0, this is equivalent in the, I read it in the correspondence before, for example, that the rep Z4 line can end at the boundary. And since this can end, and since sigma is charged, then the three-dimensional sigma operators are confined to live at the boundary and are topological defect of the boundary. And our proposal was presented that this sigma, with this boundary condition, is nothing but the duality defect. Okay? And we developed a formalism to check this proposal by computing the future rules from a bulk perspective. So this is a technical part that I will not review. And we did it in this case for n equal to 4, but then you can ask, okay, this is just one future rule. Are you sure that it is the correct prescription? So what we did was to generalize all this formalism to include a possibly infinite class of theories, class S theories, n equal to 2 class S theories in this second paper here. And in the theories also in special point of the conformal manifold, you can have several non-invertible symmetries that can be much more complicated. They can be also non-abelian, so the landscape is much more large. And there are many, many more checks that you can do. And we checked it at genus 2. We checked many examples, and we matched the future rules that we found on the boundary with those found from this prescription from the bulk. Yes.
So there's a different way to realize the duality symmetry holographically using the descendant brane.
Yes.
This sounds equivalent because descendant branes can be alternatively defined as just a sector coming from S to Z.
Yes.
Do you understand the precise connection?
There should be somehow that this 7 brane. I don't know the precise mapping between the two.
But there was another paper, as you know.
Yes.
But has this connection been made? Because this
no,
sounds
I don't
very
think
natural.
so. I don't think so because somehow it should be that this additional gate field is sourced by the 7 branes, right?
Exactly.
Is putting an integral gate field
Because that's the SO2Z subgroup that's
Yes.
preserved by this special point.
Yes.
And you're looking at just a sector of SO2Z, and that's nothing but a descendant
Yes.
brane.
Yes. Okay. Just to tell you.
But it only becomes in that case only becomes topological once you push all the way to the boundary. But you have already done that here. Like you have pushed you have pushed R to L for the dynamical degrees freedom. Only left with the topological place, right?
Yeah, I agree, but I don't think that nobody made this connection in a precise way. It seems
it should be.
Yeah. Yes.
And also just a comment, I think, for the audience that who are not familiar with this language. So when Andrea talked about what defects can end, it means that it can end in a way that preserves the topological invariance of this QFT on the slab.
Yeah, sorry. Yes, you can make it end in other ways in which and does not become.
That's right. So because in this case, for example, because A is 0, imagine you have the Wilson loop for A, you can push this bubble to the boundary and pull it off without violating topological invariance.
There are no further questions.
Just so that later he can shrink the picture without worrying about dynamical subtleties.
So you mentioned for these defects, for these topological operators, there are no local operators charged.
Yeah, I mean in the bulk.
In the boundary.
No, in the boundary there are.
There are.
For instance, if you look at Maxwell theory, F is an operator which is charged under.
But in an equal 4 case?
In equal to 4 also there are operators which are charged under S duality. You can look at the map of S duality or local operators,
Okay.
and you get
Fermions are charged.
Right, okay.
the peculiarity of this kind of symmetry is that they have the same action on local operators as S duality, but they also act on lines. So they have all these properties of S duality that you can read from like very old papers, but they are actual symmetries, and to be made into actual symmetries, you have to allow also an action on lines. And this will be actually now important for the final part of the talk, which is about the dynamical consequences of this symmetry. I will describe the anomalies of this symmetry.
Sorry, maybe related to what you said, like, so this fact that you're choosing directly boundary conditions for A
Yes.
is so that you can actually shrink the slab and go all the way to the physical.
Yeah.
Do you mean on the boundary or in the bulk?
Well, I mean, like, so you fix some topological boundary conditions on L, right? That was for B and C.
Yeah,
You start gauging the Z4, and then you put directly on A.
Yeah, let me make sure that we are not making this confusion, that there are two different things. One are the topological boundary conditions that you put in the bulk theory to make the defect topological on the boundary. And another thing was the one that I described at the beginning, that in the half gauging procedure, I had to put the topological boundary condition in the gauging of the one from symmetry to make it to make the defect to be topological. There are two different things.
Yeah, okay.
I think he's talking about the former.
But yeah, I'm talking about the.
He's talking about the former, the one on this picture.
Okay, yes. But it is not necessarily I put the Dirichlet for A. Now I put it Dirichlet to get the duality defect on the boundary. But what I'm going to do now is precisely the observation that if I put Neumann or free, let's say free, I don't know what is the correct terminology, free. So I need free A to be free on the boundary, it is still a fluctuating gauge field on the boundary, then this corresponds to gauging the duality defect.
Correspond to different topological boundary.
Still a topological boundary condition.
But it's different.
It's a different one, and it trivializes the duality defect. In this boundary condition, essentially, I'm not prescribing. I don't know where. I'm not prescribing that the rep Z4 line ends at the boundary, but I'm prescribing that it is the duality. This twist field, this twist defect, this sigma, can end at the boundary, and the rep Z4 line exists as a topological operator at the boundary. So it's the reverse. It's the reverse thing.
You're talking about boundary condition on L or R?
No, L, the topological boundary
That's
condition.
about L, okay.
So Neumann for A would correspond to gauging M. And since I told you at the beginning that anomalies can be understood as abstraction to gauging, an anomaly here can be understood as an abstraction to Neumann.
It's not Neumann probably, it's really free, right? So
Yeah, I don't know what is the correct terminology. I used to call it Neumann because it's the opposite of Dirichlet, but when you are linear in time derivatives, it's really free.
right.
It's fixed versus free.
Right.
Yes. I always write Neumann, but I'm not sure this is the correct terminology, but this is what I think.
Particularly is
Yeah. Yeah, the ambiguity is all in TFT, I think, right? And okay. So the idea is that you scan among all the possible topological boundary conditions that you have in this TFT, and if you don't find a Neumann one, it means that the defect is anomalous, right? But as I told you at the beginning, anomalies are typically classified by more subtle data beyond the fusion rules. So before I have to tell you where this more subtle data comes from in this setup, because I already described to you the duality defect as let's say, in terms of its fusion rules. But as Ivan already noticed, for instance, you have additional choices. You can put discrete torsion when you gauge. And as I already mentioned before, there is a more subtle theta which arises, and you can see it by looking at the more general case for a generic abelian group A, from the fact that any abelian group A is isomorphic to its concentration dual, but this isomorphism is non-canonical. So let me now go to the general setup. I have a d-dimensional theory with a finite abelian group symmetry, which is an n-1 form, and it's self-dual under the gauging. Okay, I introduced this slab construction motivated by holography, but this is actually more general and exists in essentially in any theory. It's something that is becoming very popular recently. It's called the symmetry topological theory, symmetry TFT. I constructed it before by starting from holography and looking at the topological sector. But this is something that you can do even without an holographic dual. It turns out that any theory T with symmetry described by C has a symmetry TFT, which I will denote by Z of C. This is a TQFT in D plus 1 dimension, which has all these properties that I was telling you before for the n=4 theory. You can put it on a slab, and on one side you have a relative version of your theory, which only knows about the local dynamics, but not on the global properties. Here you have the symmetry TFT. Here you have the topological boundary condition, which determines the global form. So it's really the straightforward generalization of what I got before from holography, but this is much more general. So let me discuss this case of the duality symmetries. The peculiar case of this duality symmetry is that on top of the zero form symmetry and the duality defect, they also have an invertible n-1 form symmetry A. So the first step is that I can start by constructing the symmetry TFT, which I call Z of C naught, for a subset of my symmetry, which is only the n-1 form symmetry. This is a straightforward generalization of what I was describing before. It's just a D plus 1 dimensional TFT, which is treated in this way. BDC is in D plus 1 dimension. Here B is again a gauge field with values in A. What becomes manifest here is that C is a gauge field valued in the concentration dual. So this theory has an n-form symmetry. Before n was equal to 2, now it's general. It can be 1 in 2 dimension. So it can be 0 in 2 dimensions. Example, d equal to 4 and equal to 1, or d equal to 2 and equal to 1. So, but in general, you have an n-form symmetry of this TQFT, which is implemented by generically ions charged under both.
You also have a choice of the Chern-Simons level
Over Chern-Simons level,
or your schematic.
here.
Yeah.
No, you do not. You don't have it because I'm assuming that my boundary theory is self-dual under gauge infinity.
Okay.
So Chern-Simons level would be an anomaly for this. So they have generically ions, they have braiding before. This is really the straightforward generalization of what I had before. But now, as I told you, to construct the actual symmetry TFT, including the duality defect, we want to gauge a certain zero form symmetry. Then you have to ask what is the zero form symmetry if we want to gauge? Intuitively, we want to repeat the same step we did before. It should be a zero form symmetry exchanging the two sides. But the two sides are isomorphic, but not non-canonically so. So what you have to do to specify a zero form symmetry is to prescribe a specific isomorphism A with concentration dual. And this specifies for you the symmetry. Indeed, you can check that using this isomorphism, you can construct a zero form symmetry, which turns out to be either Z2 or Z4, depending on whether n is odd or even. Before n was 2, and we get a Z form symmetry. For n equal to 1, for example, in 2 dimensions, you get a Z2 symmetry. Okay? The symmetry basically exchanges the two signs. There is a you have to twist it. You have to twist this exchange with a minus sign, depending on whether n is even odd or odd. So you have these two possibilities.
And for n even is always 4.
Yes. And so this phi is an additional datum of your symmetry, which should enter somehow. And moreover, as if I've already noticed before, this specifies for you the symmetry. But when I gauge the symmetry, I have an additional choice. And this choice is a discrete torsion class, which takes value in a in this cohomology group, which turns out to be always isomorphic to G. So there's two data that you have to specify to tell precisely what is this complete symmetry CFT. And these two will become data of the boundary category. What I'm claiming is that these two data.
So the statement is not true for any D, right?
I think so, yes. Remind you that G is identity towards C4.
Oh, only
it's
these
not
two
any
possible.
group, yes.
Okay. This is not
This is
true
just
for
like
general
an
model.
infinite-dimensional
Yeah,
space,
okay.
yes.
Okay.
Right, so the claim is that this phi and epsilon are precisely the more subtle data that I was mentioning at the beginning, which classify anomalies. The fusion rules are completely independent on the choice of phi and epsilon. You don't see phi and epsilon from the fusion rules. They enter from the point of view of the boundary category by more subtle, by looking at more subtle thing, which goes beyond the fusion rules. But from the symmetry CFT perspective, it is pretty clear where do they appear. And so
phi related to the Frobenius-Shor indicator.
epsilon is related to the Frobenius-Shor indicator.
I mean, in the four-dimensional case, it would be the transition of that.
Yeah, it's like a generalization of the Frobenius-Shor indicator. But
So you have four choices, you say.
yes, depends on what you want to call Frobenius-Shor indicator, because typically people want to call Frobenius-Shor indicator something which is related with time reversal anomaly on the defect.
Yes.
And in the Z4 case, it cannot be because it's Z4.
Yeah.
Precisely. So, but it's somehow related to. I mean, it's an higher analog. We call it an higher analog. The analog is not perfect beyond.
And phi is more like the bicharacter.
Phi is the bicharacter, yes. Indeed, what we did was precisely to reproduce many of the results which were already known, both in the mathematical literature and by a paper by Ivan and Brian Torgren, who discussed the two-dimensional example using the powerful tools that are available in two-dimensional, because the symmetry is described by fusion categories, which in two-dimensional are very well known and there are powerful techniques. But the point was precisely that in higher dimension, these techniques are not available. So to classify whether the symmetries are anomalous or not, we found it convenient to switch to this other formalism of the symmetry CFT, and we observed that in the two-dimensional case, we reproduce all the results which were already known, but they give you new results for higher dimension. So this symmetry CFT perspective is very useful in analyzing analyzing this kind of anomalies. And I will not go into the detail, of course, because of the lack of time and because it's very technical, but I want to mention the results. Once you fix this data, you have to look whether this normal boundary condition exists or not. And in general, this is still a very complicated problem, but the reason why it can be analyzed in this particular case with this symmetry CFT is that you can easily go from this simpler symmetry CFT, D of C naught, to the actual symmetry CFT by gauging G, but then you can also go back by gauging the dual symmetry rep G. Because this is a discrete symmetry, the gauging is always reversible, so you can go back and forth. And so this much more simple symmetry TFT, which is just a simple digraph-Witten theory, together with the specification of a symmetry G, has all the information to determine whether this more complicated symmetry TFT has or not a non-boundary condition. You just have to look carefully where this information is encoded. And the result that we found are two obstructions. The first obstruction when I say first and second obstruction, I mean obstruction to gauge the duality symmetry. So if this condition are not satisfied, the symmetry is anomalous. So the first obstruction is that Z of C naught, this much more simple symmetry TFT, has a certain Lagrangian algebra, LD, which is duality invariant. Since this is a simple theory, you can actually classify what are all the possible Lagrangian algebras in this theory and check whether they are duality invariant. And we did it in complete generality, and we found all the conditions on phi and epsilon and the abelian group such that this is satisfied or not. And we reproduce the known condition for gaugeability.
For 2D.
For 2D, yes. But
So you have the answer for 4D.
yes. Yeah, the 2D case was very useful because we had a check that what we were doing was correct. And so if this is not satisfied, then the duality symmetry is anomalous. This is a very powerful anomaly. It is very powerful because if this is not satisfied, if you have this first obstruction, then either any symmetry, any theory which preserves the symmetry, any RG flow which preserves the symmetry, either breaks the symmetry spontaneously or it must be gapless. The point is really that there is no gap realization which preserves the symmetry, and that's this the duality invariant algebra. So this is an anomaly which cannot be meshed by a gap realization preserving the symmetry. So it's a very powerful kind of anomaly. And then, if this condition is satisfied, so you have a duality invariant algebra, we found an additional obstruction, which is the following. As I told you at the beginning, a Lagrangian algebra is a way to gauge the bulk and make it trivial. So what you can do is to gauge this 0 C naught. This is a trivial theory, but since this is duality invariant, it's a trivial theory preserving G. So it's not totally trivial, it's trivial but preserves G, and it's called an SPT, a symmetry protected topological phase for G. And this is classified by Y, and Y is a group homology class, which is very hard to compute, but you can actually do it. And the second obstruction is that you notice that this Y lives precisely in the same homology group as epsilon. And the condition that we found is that Y epsilon must be 1. If this is not 1, the symmetry again is anomalous, but this anomaly is a bit less constraining in the sense that, of course, you have the possibility of realizing in a gapless phase or in a spontaneously broken phase, but for D, which is at least 4, it can be even meshed by a TQFT which preserves the symmetry.
Sorry, so Y is also determined by phi epsilon.
No. I will not enter into these details, but there are additional data which determines Y, which are not data of the category, are data of the gauging LD. And I don't want to mention things that maybe most of the people don't know, but these choices can be understood as choices of symmetry fractionalization for the symmetry. So this is an instance in which you can have additional data which determines the anomaly.
So for this criterion, you should find all possible Y's and see whether there's one Y that satisfies this problem.
Yes, you can think about this. Yes.
How much time do you need?
2 minutes.
Okay.
Right. Yeah, I just will conclude with several final comments. Okay, first of all, yeah, you can work out explicitly what this condition implies for this phi and epsilon, and you find, as I told you, the already known condition in 2 dimension. You can get new results in negative dimension. And I will just want to make several comments. First of all, this gauging of duality symmetries has been used several years ago to construct several n equal to 3 theories. Indeed, as duality n equal to 4 super Young-Mills, since it acts on the supercharges, when you gauge it, you break part of the supersymmetry, and people constructed several n equal to 3 theories by gauging as duality. But they didn't know about non-invertible symmetries, they didn't know about the fact that they didn't care much about the global structure, and it turns out that if you look at this paper, some of the theories that were constructed are actually inconsistent. You can think that they have some kind of gauge anomaly. So when you have to do with these n equal to 3 theories, you must be careful that maybe some of the n equal to 3 theories which are claimed to exist in the literature are actually inconsistent because they are constructed by gauging a symmetry which has an anomaly.
Do you mean the S-full construction
No,
or the other ones?
not the S-full construction. the discrete gauging. And then you can use this kind of constraint to say something about the IR of several deformation of n equal to 4 theories. For example, several interesting deformation which preserve duality are so-called n equal to 1 star deformations, which correspond essentially to mean mass to the chiral multiplets. They preserve as duality, and they have a huge landscape of possible IRs depending on the masses that you put, and you can work out the numbers and see what are the possible constraints that you can put. This has been done in a paper by several collaborators of mine. And there is another possible deformation which is interesting and has not been analyzed carefully from this point of view, which is the deformation with the Konishi operator, which preserves the duality symmetry. However, you cannot directly apply these results because different from the n equal to 1 star, which preserves a combination of S duality and DR symmetry such that S squares to 1, in the Konishi case, S really squares to -1 over F, because the actual duality symmetry n equal to 4 is not SL to Z, but it's called the metaplectic group. It's an extension of SL to Z, and S squares to -1 over F. And in that case, you cannot directly apply our result because this is a fermionic symmetry, and it is not completely clear to me how to extend this anomaly analysis to the fermionic symmetries. But it will be very interesting to look at the Konishi operator from that perspective because it is not really known what is the IR of the flow with the Konishi operator. I want just to conclude by saying that the general picture, which is emerging from this kind of reasoning, is that the most general symmetry in quantum field theory in the dimension is described by a mathematical structure known as a D-1 fusion category, which is a very complicated mathematical structure. Even the definitions are not completely worked out and the consequences. But the picture which is emerging is that there is a simpler description of the symmetries, which is in terms of a D+1 dimensional TQFT, this so-called symmetry TFT, which encodes all the data of your symmetry, and when your theory has an holographic dual, it can be understood as a topological sector of your holographic theory. It encodes all the possible data of your symmetry. Sometimes you just have to work a bit hard to extract what are the useful data and understand what are the consequences. So, thank you.
If there are any actual questions, review of this student session before we move over. Maybe we'll. Andrea will be around until tomorrow, so if you have more questions, you can ask him. Let's thank Andrea again for this. Very nice one.
Can I ask, just because, okay, towards the end of
Yeah,
very concretely with the very